so lab exercise 5, AC to DC conversion via a diode full wave rectifier. This is pretty much a direct application of the lecture that we just did, lecture 5.1. So in this lab, we will design and build a full wave bridge rectifier for AC to DC conversion. We will capture the time response data with the NI MyRio device, export it to a data file, import that data file into MATLAB, plot the data, derive an analytic prediction, and compare the analytic prediction to the data. Starting to, seem like that we do that part a lot, right? We capture data, we compare it to a theory. That's sort of what we try to do in the lab is to do an experiment that we think we can predict the result of and then try to do it. Great. So the objectives of this lab exercise are for students: 1, to understand AC to DC conversion; 2, to deepen their understanding of diode circuits; 3, to better learn to acquire and log data with a microcontroller board, a MyRio in this case; 4, to learn to export and export the acquired data to MATLAB; 5, to model real circuits and compare the theory and experiment; and finally 6, to learn to better plot and export plots in MATLAB. I know we've been working on some of these for a few weeks, but I think that they need repetition to really sink in. So the materials that will be needed are listed here. Kind of the usual things when you work with the MyRio. You also need to have the development environment that is the PC with Labview installed, an oscilloscope, a multimeter, breadboard, jumper wires, 4 diodes, and a 1K resistor, and a 100 microfarad capacitor. So build the circuit as drawn here. I included in the circuit diagram the source resistance, the output resistance of the function generator, because sometimes we forget that if we don't put it in there. So it's important. It's important to measure, to recognize that when we measure the output of the function generator, also we're measuring it after that output impedance, not before. Okay. So build it up and measure your resistance, actual resistance and actual capacitance. And then also measure the diode voltage drops. They should be around 0.6 volts, but in order to get a more accurate model, if you decided to go with a more accurate modeling technique shown in the last lecture, then you would be better to use the actual the measured values here. Then build the circuit on a breadboard. Be cautious with the capacitors. They're polarized capacitors, so be sure to connect the minus terminal to ground. So this is the circuit diagram notation for that. So this is the minus side. They should be connected to ground. It's okay, even though we have an AC signal, that we're going to use a polarized capacitor. The reason it's okay is that we've the way that we're flipping back and forth. So remember, when this is positive, we're going to be charging up the capacitor this way. There'll be a drop across that way. When it's negative, source is negative, then this will be higher, and it'll still charge up in the same direction. So you'll still get this high. The high side will always be on the top of the capacitor. If you didn't have this bridge in there, then you would be in trouble. You would have a capacitor that should not be loaded in reverse bias, loaded that way. So good. So do that. And then prepare the MyRio for data collection using the same method that you used before. So resource 5 is what you use to do that. So go back to that and make sure you've got it ready. Create a Labview project and main VI. So that's the next thing. So here's the thing. you can pretty much just copy the project that you did for lab exercise 3. You're capturing time data. You don't need to output any voltage in this example, but the data capture and the store and the save, all of that stuff is the same. So I would recommend just copying that over and then editing it a little bit. There's not a lot of editing that you need to do. Kind of the idea of what you're going to be doing is measuring the oscilloscope voltage and then measuring the capacitor or load voltage continuously, and then plotting them and then saving the data. So here are some front panel situations. So we're going to go through a bunch of different scenarios of like, here's the for a certain frequency for your input, you're going to use your circuit with the capacitor taken out first, which is going to look like this. You're going to get the rectification happening, and then you're going to want to smooth that by putting the capacitor back in, and what you'll get, it will look more like this. Okay, so that's, you see something that looks like this, you're on the right track. Good. So, and then here's, once again, this is the same back panel from exercise 3, once again telling you that you should tweak it. Great, so let's talk about measuring the signal. So use your VI to measure the source voltage, Vs, and the output voltage, Vout, across the load resistor. Some typography issues there. So something to note. I say to measure the source voltage, and really, once again, I'm being a little fast and loose with this. This is really Vs minus Rs, or VRS, right? Because when you measure the voltage coming from the oscilloscope, you're measuring the voltage after it's already dropped across the source resistance. Okay. Great. Okay. Set your function generator to 8 volts amplitude. For 2 cases, the capacitor included and excluded from the circuit. Measure and record each voltage in and out over at least 3 periods of the input at 10 hertz. And then do the same thing again for 15 hertz, 20 hertz, 25 hertz. So when you change the frequency, it's going to look a little bit different each time. Be sure to note which data file is associated with which frequency. Also be sure to change the file name before each trial is run, otherwise it'll just overwrite the old file. So you get done, you'll only have one file with data in it. Without the capacitor, the front panel should display something like I showed you in figure 5.7, and with the capacitor it should look more like 5.8. And once you're done acquiring the data, copy your data to a convenient directory on the computer, and you can open up MATLAB and unpack that in the usual way, same way we've done before. So, write a detailed report, a thorough description of a theoretical analysis of the circuit you should do. So it should either be a nice discussion and description of the highlights of the full analysis, or it should be a pretty detailed one of the so-called quick and dirty one. So yeah. And it should describe how the circuit works too. I mean, don't copy my words also. That's plagiarism. You can quote me, but don't quote me too much. If it's all just my quotes, then you don't have much of a report. So, yep. Also, yeah, so as part of the analysis, predict the ripple and average DC value for each circuit with the capacitor attached. Also predict the current supplied to the load resistor. Use these in the model, the quick and dirty model, to give the predicted DC voltage and ripple. So you have to do that in any case. 4 figures and that compare each other. Compare each of the capacitor attached captured data sets, input and output, to its corresponding analytic prediction. It is acceptable to predict only the ripple range and average value of the output, but a full-time analysis is even more fun. In MATLAB, be sure to use XLim to scale the x-axis such that around 3 to 5 periods are visible on each plot, or trim the data so that that's the case. Sometimes it's hard to only get like starting and stopping the front of your VI to capture that amount of data. Usually you're going to get more, so you're going to either have to trim it or use XLim to scale down your axis so you can only see 3 to 5 periods. Include somewhere on the plot the approximate measured ripple and DC value. You can use the plot cursor tool to help with the estimate. Measure, using the plot cursor tool, peak to peak and divide by 2. Alternatively, use the MATLAB function. It's cumulative trapezoidal integration, so however you want to pronounce that, to numerically integrate the voltage and divide it by the time duration, which should be an integer multiple of the signal's period, to find its average. So those are both good ways of finding that average. I mean, the second way is definitely more accurate. The first way is definitely easier. Okay. 3. 4 figures that display the capacitor detached input and output data sets. Alternatively, preferably, plot these on the corresponding capacitor attached data set plots. Carefully label and caption each of these. So if you want to put those on the same plots as the capacitor attached plots, if you can make it look good and not be confusing, using nice legending and all that, then I recommend that. I think that would be nice, but if you want to make them separate plots, that's also acceptable. 4, the other parameters measured in the lab that you're going to record as you go through, and then be sure to comment on how well your predictions matched the theory. Should be pretty good. I mean, it might be a little bit off, but we should be pretty good on this. So yeah, that is this lab exercise. When you are we're using a polarized capacitor, so of course, have goggles on, safety glasses on. These capacitors, if you connect up the bridge incorrectly, you're going to have problems. One of the reasons why I draw it like this, which is a little bit non-standard for a bridge circuit, usually they like turn it into a diamond instead of a rectangle, but I do it this way because I think this is a little bit easier to lay out on a breadboard. So try to mimic the geometrical relationships here a little bit, and be careful with your diodes to make sure they're going in the right direction. So you don't want to reverse bias the polarized capacitor, right? Something to note on the diodes, I think it's in the text somewhere, but I should just call it out explicitly. They almost look like resistors to some extent. They're a little different looking. And they have a stripe, just a single stripe on one end or towards one end. And that stripe corresponds to this. So this is the direction that it's facing. So like this line and this stripe are supposed to be kind of references to each other. So don't get confused about which direction this is going. Current is supposed to flow this way, forward bias in these diodes. Okay, that's all I've got. So good luck, have fun. See you later.